All right, I think we're good to go. Welcome back, everyone. My name is Sebastiaan. I'm also one of the developers of AiiDA Core, and a big part of my time has been spent on writing and redesigning the engine that's in the old AiiDA. And so yesterday, you've been playing around on the virtual machine where there was already data present. You imported an archive, and you've been seeing how AiiDA gives you the tools through Verdi, through the shell, through Jupyter, to interact what's in the database. But now, of course, there's a question: how do you actually construct such a database? How do you make these provenance graphs? And so the focus of today will be on this very part, and you use AiiDA's engine to produce this data, and it allows you to write workflows. So that's what we're going to be doing. And to start you off, I'm going to give you a very short introduction into what the engine does and how it's implemented and how you can use it to produce your data. So one of the core pillars, as you've seen yesterday, of AiiDA is keeping the provenance. But imagine such a provenance graph you've seen is not even that complicated. Imagine having to link all these nodes up by yourself manually would be a horrific task. And AiiDA actually, the A stands for automated, so it kind of promises you that all this stuff is automated. And that's in a sense also what the engine then does. The engine allows you to write workflows, and on top of this, for free, it will keep the provenance. And when I say free, it's free as in beer, because nothing is free except the sun rising. So there will be, of course, some amount of effort required from you, but once you've written your workflows, you can rerun them, and every time they will automatically keep the provenance for you in the background. So to describe how you do this, the various tools, we're going to start with a very simple, almost stupidly simple example. Imagine the following simple arithmetic problem. We want to sum two numbers and then multiply them with a third. I have here, I hope this is visible, this snippet for everyone. This is a potential solution in Python. So we define two functions: add, that takes two numbers and sums them and returns the result. We have multiply, that takes two numbers, multiplies them and returns the result. And then you can call these functions consecutively and you will get the desired result. So now how would we transform this such that it produce the provenance graph? Because this doesn't store anything, it's just plain Python. And then AiiDA, this is very simple. We do this through what's called a calc function decorator. And a decorator, if you're not familiar, is where you take a Python function and you literally decorate it with the @ sign and then the name of the decorator, in this case the calc function, and that alters the behavior. And what the calc function really does, it turns this into a fully AiiDA compliant processor. So the engine will understand that you're actually wanting to store this in a database. So the only thing now we have to do, in addition to this one extra line decorating the functions, we have to pass storable types. Already yesterday you encountered the concept of a node. You have data nodes. And so those are storable in a database, unlike the normal integer types. So the only thing we have to do is wrap those in the int data type. So now when we execute this line, this will actually be run by the engine of AiiDA, and for free store the following provenance. So if you now were to use the tools that you've learned yesterday to inspect your database, you would find something like this. The first two integer nodes are represented by these data nodes. They are passed in to a calc function, which is represented by this calc function node. And you see the links are drawn, signifying that they're inputs. The output is also registered. This is the sum, and it gets a create link, because this is a new piece of data that is created by calling this add function. And then together with the other input, z, what we call here in this example, we pass this to the second calc function, and that produces the ultimate result. So now you see, for very little change, just some Python code, by decorating the functions and turning your initial inputs into data nodes, AiiDA will automatically store this in your graph. A small detail, you will see that we here have x, and y. At this point, they will actually be these data nodes, but since the operators have been, like plus and multiplication, have been overloaded, we don't have to, again, wrap them here. This will be done automatically. So here we're summing not just Python numbers, but actual data nodes, but AiiDA understands what you mean, and so you can keep basically the implementation here of your functions. So, but now, of course, this is a toy example, and not all our code is as simple as just, it's not implementable in Python. We have DFT codes that are external binaries, and we also somehow want to run through AiiDA and keep the provenance. So how do we do this? Sorry, I need to explain this first. So you've already seen the term before. really what this is a directed acyclic graph. Directed in the sense that inputs go in and outputs go out. So there's a direction to the way these data are produced. And acyclic because of the causality principle. It's impossible for an output that is created to also have been an input to its own creation. So now we go forward to a more real-life example. Let's say that we cannot implement our code in Python, but it's an external code. Still, toy example, this is a bash script that does essentially the same. It reads an input file that it has two integers, two floats. It parses them, it takes the sum, and it echoes them. Imagine this being your DFT code, whatever. It takes some inputs, produces some outputs. How would you now run this through AiiDA's engine? And for this, we have the concept of a calc job. I'm not going to explain you all the details of how to implement this. This will be a focus of one of the work groups today and tomorrow. But essentially, once you've created this interface, running it through AiiDA is very similar. You define the inputs. So now, again, we have our initial x and y, the numbers we want to sum. And we need to represent this piece of code somehow, which is the load code. I think you might have already seen this. We have already code list. If you configure a code, it will show up. So imagine you configure your DFT code, and then as an input, you would pass that code that is configured for a specific machine. The nice thing is as well then, if you now pass a different code that is configured to be on another machine, the whole script doesn't have to change. Everything works exactly the same. So this makes this very transparent. And so to run it, this is this implementation of a calc job that we've called arithmetic add calculation. This is exactly what it does. It takes two integers and sums them. And this is the way to run it. Don't worry about the details. You will get to see this later on. And this is where you will start working with it. Just to give you an example that once this plugin has been made, running it is very easy. And again, if you run this, what will be generated by the engine in the background is this provenance graph. So you'll see the three inputs here. We have the two integers, and the code node, because that is also part of the inputs. We have a calc job node that represents the execution of this calculation, and it produces the result, which is the sum, but also this retrieve folder. You should have seen this concept yesterday, when you do verticalc job ls and verticalc job cat. That will allow you to inspect basically the raw files that have been produced by this calculation. In this case, this is just the standard out that has been echoed to an output file. So the advantage of these calc jobs is that they can be run on remote machines. The calc functions you run on your local machine in your interpreter. But these calc jobs you can run on remote machines that connect through SSH, through job schedulers. Again, you configure this once through the code. And so then if you change a machine that uses Slurm or Torque or we have lots of plugins, you don't have to change anything here. AiiDA will take care of it. And as I said, the implementation of such an example will be the focus of one of the work groups tomorrow. So now if we go back to our initial provenance graph generated by a calc function example, you see that there's an individual sequence of the calculations is recorded. So we have our addition here and we have our multiplication, but it doesn't really say how or why this has happened. Now this example is a bit silly, but imagine you have an actual workflow that has many steps, many calculations. There's always some sort of logic why you do a certain calculation, and based on those results, you go to another. And so this is where workflows come in. Because workflows allow you to define this logic and basically allow you to rerun it, and then they will also keep the history. So an example of a workflow, just like the calc function was the decorator to write calculations in AiiDA, the work function decorator, so spelled almost exactly the same, is an identical concept, but instead of calculating stuff, it defines a workflow. So let's imagine the exact same problem. So we want to add two numbers and then multiply by a third. So again, here we have our calc functions that we wrote before. And now we write a work function that captures that we first are going to call the add function to get the sum, and subsequently use that result to call the multiply, and finally to get the product, and then we return the product as a result. Calling it is now simple, it's just only one function. We only call the work function. And the provenance that is generated is the following. So it's a little bit more detailed and complex than the previous one, but the nice thing, so this is the execution of the work function representation. And so the nice thing is that you now can select also sort of granularity. For example, you can hide the details within the workflow and only focus on the workflow itself. So if you just hide all the pink calculation nodes, you get this picture, where you just pass 3 input nodes through your workflow, and it produces a result. But likewise, if you hide all the workflow logic, the logical provenance, you get back exactly the original result. I mean, in terms of the data, nothing has changed. We still summed 2 numbers in add, and then took the sum with a third one, passed it to multiply, and that was the final result. You can convince yourself by looking at this graph that essentially these are 2 representations of exactly the same thing. So again, implementation is very simple, very easy to transform your work into a work function. But also work function is an overly simple example. It's not going to be a good fit for real life situations. And for this, we have the concept of work chains, which do exact same as work functions, but are a lot more powerful. This is an example of how we can do the add and multiply problem in a work chain. I don't want you to focus too much on the syntax. This will all be explained today during the tutorial, but this is just to demonstrate the concept. The work chain has this define method, which already gives you a nice overview of what it's going to do. It defines that it takes 3 inputs. In its outline, it says exactly what it's going to do logically. We're going to do an addition, we're going to multiply, and then we're going to record the results. And here, the output is going to be 1 result. And so here in the implementation, you can see that we actually just call through to these calc functions that we've done. So here in the add step, we simply call the add function, passing our inputs. And we store the result temporarily in the context. You will see this concept later. And then the second step, we will take that intermediate result and call multiply with the other input. And finally, here we record our result. Executing this through the engine will yield this. Now, this should look very familiar, because this is almost exactly the same as the work function example. The only thing here is that we changed the representation of the node. This is a work chain node, this is a work function node. It's to be able to distinguish between the two, but functionally they're identical, they're perfectly the same. So why go through all this extra trouble to do work chain instead of doing the simple thing, the work function? The reasons are that the work chains can be submitted to the daemon. And since a daemon is a process that runs somewhere else, and you can run multiple of those, you can submit these in parallel, as many as you want. So imagine you want to launch, like Stéphane Cotonnier explained in his example, where you need to launch 1,200 calculations. If you submit them to the daemon, you can submit all 1,200, and the daemon will start working on those in parallel. With the work function, it runs concurrently, blockingly. You can only do 1 at a time. Additionally, you see here those steps in the outline, so add, multiply, results. Progress is saved between each of these steps. So let's say you're having, in each step, you do 1 big calculation. After every step, the progress is saved. So if something happens to the machine, your computer crashes, you don't lose all the progress. You can simply, the daemon will restart from where it left off. Imagine if you did this in a work function where you do all these big calculations in sequence. If your computer crashes, you lose all the progress up to that point. So again, for real life situations, you probably want to use the work chain. This define method gives you a nice overview and programmatically of what it's going to do. And we have certain tools to automatically produce documentation online for this. So when you write your work chain, you can use this plugin and it will automatically format this into HTML readable documentation. And it gives a user an overview of what's going to happen, what the goal is of the work chain, without having to read every line of implementation and code, which is very nice. And as a whole, this work chain captures the scientific knowledge. Like you put all the logic in there, based on some results, I want to go there, I want to run a different calculation, and you can give this work chain to somebody else, and they can run it with different inputs, and they don't have to do anything. And what's more, I think that's one of the most powerful things, that these work chains can be used as modular blocks. We'll see, I will give a talk later today, more on the details of the implementation, once you've implemented one yourself and you're a bit familiar with it, how you can easily wrap these work chains in like a bigger workflow. And this allows you to make very well-defined, robust workflows that then for higher level workflows, you reuse. So all the logic that's captured in here, you don't have to type again, you can use those again, and this makes for a very powerful system. All right. So there's one big caveat that might be a bit tricky to understand initially in AiiDA, and I'm going to try and explain this. It has to do with, I've talked about calculations and workflows. And so in AiiDA, workflows cannot create new data. And doing so, if you do so anyway, you will lose provenance. And the easiest way to demonstrate this is by an example. So let's take our first example again, 2 numbers addition and multiplying with a third. But now the line, maybe goes back to the previous example. Here, this work function called the two calc functions to do the actual job, to do the actual calculation. Now let's instead do the addition through the calc function, but then do the multiplication ourselves within the work function. This would be the resulting provenance, and I've drawn here an imaginary link between the sum and the final result, because this link wouldn't be there. And you might think, why is this a problem? In a sense, it is a problem because this product, so this final result, is dependent on this intermediate data point, but there's no physical connection there. So in a sense, you're losing provenance. You can think this might be covered by this node. It's implicit, it's hidden within this. But as soon as you start writing more complex workflows, this becomes more difficult to see, and in a sense, you're losing provenance. So that's why when we say workflows cannot create new data, in a sense here, this new product is created within the workflow, and that is not represented in the provenance graph. It's not necessarily what you want. So then you might ask, well, why don't you just give the workflows the power to create? Simple. I mean, as soon as somebody does this, also draw a create link to make sure that we have a link through this guy. And this has to do with the fact of this return link. In the very beginning of AiiDA, we had only calculations, and you could only have create links. But we realized doing every calculation by hand is not sustainable, so we need something like a workflow. But if your workflows become huge and have lots of calculations, you also don't want to have to go sifting through to one of the results of the calculations. You want the workflow to be able to return the final result. Even though it didn't create that result, but one of the calculations did, you want to just return the result as a shortcut. So that's why we had to introduce this return link. But that introduces a problem, because with the return link, imagine the following work function. We call it maximum. It takes 3 integers, and all that it does, it just sorts them and then returns the last one. So essentially, it gets you the highest number. So if you run this, the provenance graph will look something like this. You have your 3 inputs. They go inputs, and then the workflow selects the highest one. Remember when we talked about the DAG, the directed acyclic graph? We now have a cycle. And this is because of the return link. The return link basically breaks the causality principle because it's different from a create. We could have opted to basically say, okay, we no longer have a DAG. But the DAG has nice properties. If you think about data provenance, it allows you to reason about where data comes from. And so it's a very powerful and important concept, and we wanted to guarantee this. And the only solution was to basically then split the calculation and the workflows in 2 different worlds. Because that then guarantees, as I showed before, if you only consider calculations, their create links and output links, you're guaranteed to have a DAG. And as soon as you include the workflows which are useful for other purposes, you no longer have this criterion or this assumption. So that's why we have this what might seem a bit odd at first, this very hard, strict separation between these 2 types of processes. Because again, these are both processes. To summarize, calculations can create new data. And workflows, they can call other processes, so other workflows, other calculations, and they can return optionally the data that have been created by those processes as a shortcut. Now, this is a bit weird concept, and you will see this throughout the tutorial as well. If you have questions later on, then feel free to ask. So this then sketches the whole graph ecosystem of AiiDA. These are all the different nodes that you can see. We've introduced all of them. These are the 2 different calculations. So through the calc job node, that represents an external piece of code. And the calc function, which is just a snippet of Python decorated by the calc function. And likewise, the work chain and the work function. And then green is data. And this is just a made-up graph to see what it looks like. You see the different links as well. So very quickly, the OverM hierarchy. This is then why already yesterday you saw the difference between, and everything in the graph is a node. And it's split at the topmost level between process nodes that represent the execution of a process. And then the other, you have the data, which have various subclasses. And so here you then see where these work chain node, work function nodes, and other classes fit in. These are only really necessary for you to know if you want to then go back. You have already run your workflows and your calculations, and you want to query your database. Let's say you want to find all the work chains in your database. You couldn't use the process node because that will match also all the calculations, the calc functions. So that's why you then would use this specific subclass, because that gives you a way to target only a subset of the graph. All of this is explained in the documentation for reference. I just wanted to give you an idea of what this looked like. But this is mostly important only if you then go query your database afterwards. Similar is a link hierarchy. Create links will only exist between calculations and data, because calculations are the only classes that can create data. And workflows in parallel only have return links. And these are call links, showing that also only workflows can call other processes, and calculation cannot call another process. So this is a quick table to summarize. We have the calcjob class that produces when executed a calcjob node, and these are the calculations that are performed by external codes, anything that you run on a scheduler as a binary, for example. The work chains are the most advanced way of writing a workflow. They will create a work chain node, and so exactly that is to define a workflow that runs multiple processes. And these are the classes corresponding to the calc function and work function decorator. Now, as I said before, everything is a process. All these things in AiiDA are called a process. And they have a process state. Yesterday you did Verdi process list. It showed you a list of the processes that have been executed in your database. And they were all finished because you had imported and they were all already done. But there are other process states. There's a difference between active states and terminated. So active is, well, the process is still active. Can be, in the beginning it's created. While it's running. And if it's waiting, it could be waiting on the scheduler. It could be waiting on another process that it's waiting for. And then these are the three terminal states. So killed is if you personally kill it, or a parent kills it. Accepted if really an exception happens, some bug in the code. And finished is when everything goes okay. Mind you, that finished doesn't necessarily mean that the result you were looking for is also correct. So finished just means there were no exceptions during execution of the process. Let's say if you're running an SCF convergence calculation, if it reached convergence, it's finished, and then in that case it's successful. But imagine that it didn't converge. You might then decide to say that it's finished, but it's not the result I was looking for. And for this we have the exit status. This is a common concept in programming. A piece of code can return an exit code, and typically if it's 0 means everything was okay, and if it's non-zero, an integer is saying there was some kind of a problem. And the same works in AiiDA. If it's finished and the exit status is 0, means all good. And if it's non-zero, it means there was some kind of a problem which corresponds to a specific error. This is up to the developer, and you will see this later in the tutorial, how you can use this to communicate problems. And these are all these handy properties that on a process node, you can ask whether it was killed, whether it was terminated, whether it was finished and failed, etc. Then, processes. For this is maybe interesting for people who have experience with an older version of AiiDA. When I hammer on everything is a process, because in the old AiiDA there were also the concept of calculations and workflows, but they were all designed differently. You had to work with them differently. You had to launch them differently. They had different commands. And with AiiDA 1.0, we homogenized everything. So now everything is processed. So launching all these things is exactly the same. And there's 4 ways of launching a process. You have the 3 run methods, and you have a submit method. Run means run in my local interpreter, so we'll be blocking. And as I explained before, submit means submit it to the daemon. So you will regain control over your interpreter straight away. You can start doing other stuff. And this will send effectively a task to the daemon. Say, okay, you take care of this, you start running the process. And the way these work, because you will see these in the tutorial today, and I wanted to give you a quick overview. All of these launchers have the following syntax. You call them, it's a free function. The first argument is the process class, so it can be the calculation, can be the work chain. And then the input you pass is keyword arguments. So this we have already seen, the arithmetic add calculation. In this case, we're going to submit it to the daemon. We pass the process class, and we say input x equals this integer, and input y equals this integer. And this will return a node that represents the execution. Note that it doesn't have the result yet, because it goes to the daemon, and the daemon needs to start running it. But you can inspect through the node its status. You can do .isFinished or it is terminated. And of course, you can always use Verdi process list to see what's going on. Now, instead, if you want to run for testing something locally, because then also all the output, all the logging will happen in your screen, and you can see it running, as it were. So this is usually for big calculations. You typically don't want to run. You always want to use a daemon. But for testing, if you're writing your code and you quickly want to test locally, you can use run. And it has exactly the same syntax. Again, the process class and then the inputs. And this will actually return a result, because this will wait for the thing to be finished and then give you the result. Sometimes you also want to have, like in submit, a reference to the node though, because here you will have a result, but not the actual node that represents the execution. In that case, you can use either run get node or run get pk, and instead of only the result, they will also return the node respectively or the pk. And this then you can use to reference it in Verde process list and what have you. As a shortcut, you can only import run, and instead of having run underscore get node, you can also do run get node, run dot get pk. This is just a useful shortcut. It works the same. And then finally, let's imagine you have lots of inputs and you would have an enormous line. You can use Python syntax. You can instead just define your inputs in a dictionary. So here we define x and y as our inputs, and then you can use the * syntax, which is just Python syntax, which basically expands this dictionary in the keyword arguments that we expect. So this is useful if you start building huge dictionaries of inputs. It's easier to have them line by line. And I think you might have already seen the process builder. I'm not sure. The process builder is exactly the same, where you get the builder, you assign your inputs, builder structure, and then you just have to do a submit builder, and it works exactly the same. All right. So I already mentioned this. What happens when we submit a process? We send this off to the daemon. So how does this actually work? I won't go into too many details, but I think it's important to have a little bit of a sense of what happens behind the scenes. So when you submit a process, you locally construct a little daemon worker and stores the node in the process. So let's say we run a calc job. The first thing it does is creates the corresponding calc job node in the database. That will be its reference. And the next thing it does, it sends it to RabbitMQ. RabbitMQ is like is a service that has to be installed on your machine. And think of it as a mailman. You send it messages, and it sends then the messages to somebody else. So it's not going to run it. The process itself, it just sends this task and says, OK, I've created this node. Somebody else take care of this. So what happens with those tasks? As I said, RabbitMQ is like the mailman. He gets all these tasks in a queue, and he starts distributing to the various daemon runners that you have active. You have, in principle, not unlimited, but you can have many of these workers running in parallel. So when you start the daemon, he will launch one, but you can add multiple and as many as you want. And so RabbitMQ will start distributing these to the daemon workers, and they will then actually start working on your process. And that's what makes the new AiiDA engine so fast and high throughput, because they can work independently, and they can actually handle multiple processes at a time concurrently. So that's one of the big changes in the engine. And why do we use RabbitMQ? Because RabbitMQ is a very, very mature project and makes a couple of promises. All the tasks that we send are persisted to disk, which means that if you shut down, you submit a bunch of processes on your computer. When you shut it down, those aren't lost. When you then restart your machine and you restart the daemon, they will continue where they left off. And so RabbitMQ makes sure that it saves those. And each task is guaranteed to be delivered, and only delivered to one. So it will make sure that every task that it gets will send it to a worker, and will start working on it. And it will resend it until that task is complete. So until it gets the confirmation from the worker, OK, it's done, I've completed it, it will start to keep resending it. So this gives us basically the possibility to run multiple processes in parallel independently. And we will make sure that even if your machine dies or the remote dies, as soon as it at some point is restarted, it will automatically restart all processes, and it will be finished. Right, so almost at the end. Verde process. For everything that runs, everything that you launch, Verde process is your one-stop shop. You've already seen this yesterday. If you launch processes, you can do Verde process list, and by default, it shows all the active processes. So for example, here we have a bunch of relaxed work chains that are in the waiting state. I haven't shown anything, but they're waiting for their sub-workflows to finish their running. Here, for example, a PW calculation is also waiting because it's waiting for a transport task. It's waiting for the scheduler to tell that it has completed. It will query the scheduler now and again. So is this task done yet? And if it's done, it will start retrieving it. We have Verde process status. As I said, workflows in AiiDA allow you to build nested workflows. You can make them modular. You can reuse certain components. And that nesting will also be shown in Verde process status. So for example, here I have a relaxed work chain that will call a base work chain, and that one will then actually call a PW calculation to do the work. And the relaxed work chain does this multiple steps. And so for each one, you can see what the status is, or if it's done, and the PK, which allows you then to further inspect. Then there's also the method of logging. So sometimes you want to show to users while workflow is running what is happening actually. And this is done through logging. So these are human readable messages. And this is to then say when a calculation of workflow has finished, you can do Verdi process report, and it will also again show a nested, indented version of what's happening. And it literally says, okay, I'm launching this base work chain, and the base work chain then says, I'm launching this calculation. Calculation is finished, work chain is complete, and this is like a human readable log. Then there's a couple of ways, since these processes are actively running, you can interact with them over RabbitMQ, because they might be with a daemon worker. And so you can also pause them while they're actively running, and you want to pause them, could be any reason. You can pause the full Verdi process pause, and this is then the PK of the node. Play, you can resume them, and you can kill them if they're active. As long as because if they're no longer active, then it says it's already terminated. Or if it cannot actually reach the task, you will get this warning. Now, why is this pausing? This pausing is not just for you to pause certain things, it's also used by the engine itself. Because one big improvement that we had over the old engine is, imagine you have these job calculations that run on a scheduler. So they need to, for example, submit the calculation to the remote over SSH. They need to query the scheduler to get its status. They need to retrieve all the files when it's done. And during any of these processes, the connection can die. Your machine can lose internet. The cluster can go down for scheduled maintenance. And the old AiiDA, then those processes would just fail. They would crash. Basically, your calculation was gone. The new engine is a lot smarter. And when it fails, it will reschedule the task. It says, oh, listen, the SSH connection failed. I couldn't connect. I'm going to try again in 20 seconds. And if that fails again, it reschedules, but then a bit later. And finally, after 5 attempts, it will say, I couldn't do this 5 times in a row. I'm going to simply pause the process. And I'm going to put this message here. So in this case, the retrieve calculation failed for 5 times. You as a user will see this then, and you can then react and say, I lost my connection locally, or the machine was down for maintenance. And as soon as it's back online, you do Verdi process play with the PK, and everything continues where it left off. So this will make sure that even if your calculations on the remote are done, and you spent a lot of computational resources, if there's some temporary problem, you won't lose all that progress. So that's also why this pausing mechanism is very, very important. If you now start running in high throughput mode, what AiiDA is also designed for, that you launch lots of calculations, which I started doing this summer, and then CSCS called me and they said, please stop harassing our cluster. Because AiiDA is now too fast, and we were submitting way too many jobs and connecting way too fast. So to still make this compatible with AiiDA, we introduced some throttling mechanisms. So instead of every process independently connecting to the machine, the daemon will bundle all this and only do it, let's say, every 60 seconds, every 2 minutes. And this is configurable. So depending on the requirements of your cluster, you can say only connect every 60 seconds, or if they're very nice and you don't care, say every 1 second. So this is configurable. And this is what you've already seen when you configure the local host, the save interval. So for the local host, we don't care because it's our own machine, so we set it to 0. But for SSH machines, you might want to set it to something else. Currently, this is a relatively new feature. This can be done in the API, so you can load the computer. In this case, would then maybe an SSH computer, and you can get the minimum job interval. This is actually a second throttling mechanism that on top of the transport that it opens, it also limits the calls to the scheduler, the SQ command for, like, let's say, Slurm. These are all a bit advanced. I just wanted to mention them to you. If you have questions about this later, come find me. Just wanted to show that this exists in AiiDA, and this allows you to use these. All right. Some acknowledgements. I have to apologize, it's not complete, but you've seen all these people here, and with that, I would like to take your questions. Are there any questions? If not, then I think Oscar.
So, you mentioned the concept of daemons in a daemon.
Yeah.
Could you explain the difference and probably explain how AiiDA communicates to the daemon so that the daemon...
Sure. So it's a very good point. I mentioned daemon and daemon worker, and a bit interchangeable. When you do Verdi daemon start, you run a daemonized process, which we use a library called Circus, and that will launch one daemon worker. So the daemon's responsibility is that if that worker dies, it will just relaunch it. But it doesn't actually run anything. It's the workers that will run the processes. And that's why you can also launch multiple. You will then ask the daemon, launch more of these workers, and they will each individually, independently start working on the processes. And the communication happens just like if you submit a process, it goes to RabbitMQ, and RabbitMQ then sends it to the workers. They also use RabbitMQ to talk between themselves. Like if they're running a process, and the process is finished, they send a message to RabbitMQ says, and this process with this ID is now finished, and anyone that was listening for it, like process sometimes workers are waiting for another process to finish, they subscribe as a listener. Instead of having to poll and query if it's done, they will get the message from RabbitMQ and they can continue straight away. So this is what's called event-based messaging instead of polling, which is also part why AiiDA is a lot faster, the new daemon, compared to the old one.
Is there also a possibility to limit the number of processes the daemon tries to spawn at the remote machine?
The total number of processes.
Yes.
There's no built-in number limit to say, okay, only run 100 jobs at a time on this machine. But we are thinking about implementing something like this. Yeah. Of course, you can do this now manually. You have you have to launch the processes anyway. You can query your database because you have the process node in your database to represent that process on the remote. And so you can query how many do I have now, and if they exceed a certain number, you just don't launch new ones. So it is already possible, but it will require some effort from you in your launch script. But we are thinking of incorporating this in AiiDA core itself, and setting it as a variable.
I wasn't really clear why the processes were decoupled from their nodes. Like, do I actually write two separate queries? Couldn't the node been like an attribute of the process? Could you maybe clarify the distinction and why it was necessary?
Yeah, so the process, I've explained it, I just came up with this analogy. I'm not sure if it's very clear, but think of a process when you implement the work chain or the calc job, it's like a recipe for a cake. It describes how the thing should be made or how it should be run. But then when you actually make the cake, you have a separate instance of the cake. You can bake it again, following the same recipe, you have a second one. So the recipe is in a sense the process which describes how the thing should be run, and the node is then a record of an execution of that process, right?
So it's like a class object distinction.
More or less, yeah, but they're separate classes, so you would interact with them in a different way. And the process node is what's recorded in your database, your graph, as a record of that you actually did execute this process. And the process, while it's running, is a Python instance that sits in memory. You cannot even, and it might be with a daemon, so you cannot even, ask it to do things because it's living in a different Unix process. And so that's why we have Verdi process, because that will go through RabbitMQ, find the correct process, and will tell you to do certain things.
So if I'm doing a query, do I only have to think of one of them, or do I have to think of two?
When you do queries are only ever on the nodes. Because when you query your database, which is the provenance graph, so you only interact with the nodes. You never interact with the process itself.
Okay.
Sorry, there's another question. I will come to you afterwards. Yeah.
I have a question. When we submit bunch of jobs
Uh-huh.
to daemon, and then it basically communicates with the in front end of HPC.
Mm-hmm.
And then if we have a line running job and we want to see the log file of the calculations when it's running on the calculation,
Mm-hmm.
is it possible through AiiDA, or we should just connect to the front end?
So there is one way, and there's a command called Verdi calc job go to computer, which basically will then so you just need the PK of the process that's running, and if you do Verdi calc job go to computer this PK, it will open through SSH a shell to that machine and bring you to the running directory, and then you can just use ls anything you want to see the progress. But effectively, it's just like going to the remote machine and actually checking. There's no command that does it interactively and fetches it for you, just displays it. But in a sense, it's possible. Yeah. Yes.
So when you make a workflow, then you wrap up some logic inside that has to be done by your local computer,
Mm-hmm.
and then there is the part where you submit it, and there is your computer that is managing the connection between the HPC, the cluster, and everything.
Mm-hmm.
So the thing is that when you start to have a lot of jobs and there is the weight of what has been done on your computer inside the work function and this managing of things. How does AiiDA manage these two things? So it does first all the logics and then submit everything. It does little by little. And when you test it for high throughput, how many calculations are you speaking about? Thousands, hundreds?
So this, okay, so let me answer the first question first. So what it does, I mean, any daemon worker can run multiple processes at a time. It will not do this actually concurrently using threads, because AiiDA is not thread safe, but it will use async programming. So we'll take one process, do whatever it can do. Let's say it then gets to a calc job that needs to be done. At that point, it cannot continue, it's waiting. It then pops off that process and takes the next one. And so these are all in queue internally, and it so does whatever it can do, and it's working constantly. Unless it's waiting, and then it will have a timeout, a wait for the message that is done. So that's how that is done. But yeah, you're right. So all the logic and all the computing that is happening in the work chains themselves are done on the machine where the daemon is running. So if that's on your local machine, you have your AiiDA instance there. It's your computer that is performing those calculations, those computational load, and the calculations are then offloaded to the cluster.
And just the thing, I mean, imagine that of course depend on the heavy and the logic on the workflow, but imagine we have a very simple workflow. Managing this thing, managing just the connection between computer is still doable for thousands of calculations.
Oh yeah.
Okay.
Yeah. And so to give you an idea, I have my own high throughput project that I ran on the latest version of AiiDA. What I did basically was download a whole bunch of CIF files, let's say 400,000 from an external database, and my goal was I wrote a work chain that will take a CIF file, run 2 calc jobs that wrap the COD script, that basically do some analysis on the CIF and prepare it. So I run 2 calc jobs and then a calc function to parse the CIF into a structured data and primitivize it with seekpath of the library. So those essentially per work chain, you have a total of 4 processes where 2 of them are calc jobs that really go to the whole scheduler business. And I was able to run roughly 100,000 of those. I did 400,000 in a day. So you can get on the order of 50,000 processes per hour.
You get your computer stuck or?
No.
Okay.
It's just, I mean, it's getting hot. It's doing a lot of, but the bottleneck, let's say the top limit for the engine, like all the overhead of treating this like processes, managing them and sending messages, I don't think that is going to be the bottleneck, because with this I showed that you can really go to lots of processes, because typically what we will do, all the bulk of the computation will happen on clusters and goes to SSH, and we'll just have to wait for the queue to allow our job and for the job actually to run. So that will be probably the actual bottleneck, just waiting for the queue and it to be done.
Thank you very much.